Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. Tonight we are going to finish our discussion on acids and bases. That's right, there is a light at the end of the tunnel. I think I started this acids and bases live stream series way back in early June, and here we are in August and we're still not finished. But by the end of this stream tonight, unless anything crazy happens, like my kids wake up in the middle of the night and scream or something like that, we are going to finish this topic. So with that, I present to you Acids and Bases Volume 9. If you are at all interested in watching Acids and Bases Volumes 1 through 8, you can visit my Acids and Bases live streams playlist. There's a link down there in the description. And as always, your feedback is more than welcome and highly encouraged. So please, if you're watching this live, feel free to drop your thoughts in the chat. And if you're watching this as a video, please feel free to leave a comment. Without your feedback, I am lost. All right. So we're going to start by reviewing the content from last week, which was Acids and Bases Volume 8. And last week's stream was all about the acid-base properties of ions and salts. So we looked at anions, which are negatively charged, of course, and cations, which are, of course, positively charged. We looked at them individually. Anions can behave as weak bases, and we saw last week that if your anion is the conjugate base of a weak acid, then that anion is itself a weak base. And if your anion is the conjugate base of a strong acid, then that anion is pH neutral. So your anion will either be weakly basic or pH neutral, depending on what it's the conjugate base of. And we also looked at cations, which behave as weak acids in some cases. And I'll go ahead and reduce myself here and get out of the way. Okay, looks like I'm out of the way. All right. So remember, with cations, we basically have three categories. We have cations that are the counter ions of strong bases. So that would be like sodium ion, lithium ion, calcium ion. Anything that's a strong base, the cation that's paired up with hydroxide in that strong base is considered the counter ion of a strong base. Those are pH neutral. The other category is cations that are conjugate acids of weak bases, and those are weak acids. And then finally, we have cations that are small, highly charged metals like iron, like aluminum, things like that, and those behave as weak acids. And of course, if you want more detail about that, you can visit the playlist and locate Volume 8, and that will answer any questions that you might have. And then we talked about the acid-base properties of salts. And remember, with salts, a salt is simply an ionic compound, a collection of cations and anions that overall are charge neutral. And with a salt, you basically just have four possibilities. You either have both your cation and your anion are pH neutral, in which case you will have a neutral solution. Another possibility is you have a cation that is weakly acidic and an anion that is neutral, in which case you'll have a weakly acidic solution. The third possibility is your cation is neutral and your anion is weakly basic, in which case you will have a weakly basic solution. And the final possibility is that you have a cation that is acidic and an anion that is basic, which might be acidic or basic solution, depending on the relative strengths of the acid and the base. If the Ka for your acid reaction is larger than your Kb for your basic reaction, then you'll have an acidic solution. And if the reverse is true, if your Kb is larger than your Ka, then you will have a basic solution. So that was the material from last week. So again, if you want to check that out, I would highly encourage you to do so, of course. So we're going to go ahead and jump right into the content of tonight's stream, which is all about acid strength and molecular structure. So I really like this topic because it really takes a stab at answering the question of why do some molecules behave as acids while others don't, and why are some acids weak and some acids strong. So we're going to take an attempt at answering these questions. So for instance, why is hydrogen sulfide, H2S, acidic while methane, CH4, is not acidic? I mean, after all, they both have hydrogen. We know that under the Bronsted-Lowry definition of acids and bases, an acid is a proton H plus donor, so they both have hydrogen. So what is it about H2S that makes it acidic, while CH4 doesn't have that same property that H2S has that makes it not acidic? So we're going to talk about that. Another question we could ask ourselves is what's going on at the molecular level that is responsible for, say, HCl, hydrochloric acid, being a strong acid, while HF, hydrofluoric acid is a weak acid. So we're going to talk about all of those things coming up. So we're going to divide our discussion talking about two different types of acids. One type of acid is called binary acid. A binary acid is simply hydrogen bonded to one other element, so HCl, HF. Those are prime examples of a binary acid. And then the other type of acid that we're going to talk about is an oxyacid. So an oxyacid is when you have hydrogen bonded to an oxygen atom, which is then bonded to another atom or group of atoms. And so examples of oxyacids would be like nitric acid, HNO3, perchloric acid, HClO4. So we're going to divide our discussion talking about binary acids and oxyacids, discuss each of them individually, starting with binary acids. So I'm going to move myself over here briefly. And with binary acids, there's really two factors that determine the acidity or acid strength of the acid, and they are bond polarity and bond strength. So these are topics that, if we're coming into this acids and bases topic, we should kind of have an understanding of. But if you don't have an understanding of bond polarity or bond strength, I do have a couple of videos, and I've included links in the description to those videos. One of them is called What is Electronegativity, and the other one is called Nonpolar Covalent, Polar Covalent, and Ionic Bonds. And so if you're a little fuzzy on those topics, electronegativity, bond polarity, things like that, then I truly believe that watching those two videos would really, really help to bring you up to speed. So, all right, so in order for something to be acidic, right, it needs to be able to donate a proton, right? It needs to be able to donate an H+. And in order to donate an H+, the bond between hydrogen and the neighboring atom must be polarized, which means that there must be a significant difference in electronegativity between hydrogen and the atom to which that hydrogen is bonded. Electronegativity, just briefly, I'm not going to reteach the whole concept of electronegativity in this stream, but electronegativity, in short, is the ability of an atom to attract electron density to itself in a chemical bond, right? And so when you have two atoms bonded together with a significant difference in electronegativity, you have what's called a polar covalent bond. The bond is polarized. So these two electrons that make up the single covalent bond between hydrogen and the neighboring atom are not shared equally between those atoms when there's a large difference in electronegativity. One of those atoms, which we're calling it just X, we're just using this generic label of X to describe the atom to which hydrogen is bonded. If X has a much larger electronegativity than hydrogen, then it's going to form this polar covalent bond, which will give X a partial negative charge, and it will leave the hydrogen atom with a partial positive charge, right? And so having that partial positive charge for that hydrogen is good when it comes to acidity, because in order to be able to donate a proton, right? Think about what a proton is. It's a hydrogen atom with a full positive charge, right? And so having a partial positive charge on that hydrogen prior to that acid-base reaction facilitates the donation of a proton to a base, right? So in other words, in order for something to be acidic, there must be a polar covalent bond between hydrogen and the atom that hydrogen is bonded to. So earlier we talked about, well, why is H2S acidic and CH4 is not? Well, the hydrogen-sulfur bond is quite polar, and the hydrogen-carbon bond is virtually nonpolar. Hydrogen and carbon have similar electronegativities, right? So you must have a polar covalent bond in order for it to be an acidic molecule. So bond polarity, that's one of the two factors that influence the acidity or acid strength of a binary acid. The other one is bond strength, and we're going to jump to that in just a moment. But just briefly, if we look at just talking about bond polarity here, so if you have, for instance, hydrogen bonded to lithium, right? Lithium is actually much less electronegative than hydrogen. In general, metals are much less electronegative than nonmetals. And so this is not acidic because this bond would be polarized toward the hydrogen. In fact, the difference in electronegativity between hydrogen and lithium is so large that it's an ionic bond. It's not even a polar covalent bond. So this is definitely not acidic. A hydrogen-carbon bond, anything with a carbon-hydrogen and nothing else, that's not going to be acidic because, again, there's no significant difference in electronegativity between hydrogen and carbon. This is virtually a non-polar covalent bond. However, if you have HCl, right, there is a significant difference between hydrogen and chlorine, resulting in a polar covalent bond. This hydrogen atom carries a partial positive charge, and as a result of that, HCl is an acidic molecule, right? So bond polarity. The other factor that influences acid strength is bond strength, right? So in other words, how strong is that bond between hydrogen and the other atom, right? And this table here sort of looks at three acids individually. We have HF, HCl, and HI. So in one column, we have their bond energies in kilojoules per mole. And the higher the bond energy, the higher the strength, because bond energy is simply the amount of energy that it takes to break the covalent bond. And then in this third column, we have acid strength. So notice that as the bond energy, right, decreases, the acid strength increases, right? Why is that? Well, if your bond energy is high, if your bond strength is high, right, then that means it's going to take a lot more to dislodge that hydrogen and donate it in the form of a proton. So the weaker that bond is between hydrogen and that other atom, the stronger the acid it's going to be, because it's going to take much less energy to accomplish that acid-base reaction, right? So bond polarity, bond strength, those are the two factors that influence the acidity and acid strength of a binary acid. So now we're going to talk about oxyacids. So for an oxyacid, we can just consider this general formula here where you have hydrogen bonded to oxygen, and then that oxygen is bonded to another atom that we're going to call X, and then that also has some other stuff bonded to it. Maybe it does, maybe it doesn't. But there are two factors that affect the acidity of an oxyacid. One of them is the electronegativity of X, the atom to which the oxygen, which is bonded to the hydrogen, is bonded. And the other factor is the number of oxygen atoms that are bonded to X. So we're going to talk about each of these sort of bullet points in more detail. So let's first talk about the electronegativity of X, right? So here's another table where we have three acids here, HOCl, HOBr, and HOI. And in this middle column here, we have the electronegativity of the atom Cl, Br, or I, reported, that's on the Pauling scale. And then over here in this third column, we have the Ka, the acid dissociation constant values associated with these weak acids. So notice that as the electronegativity decreases, right, chlorine is more electronegative than bromine, which is more electronegative than iodine. What happens to the Ka value? Well, it looks to me like the Ka value is decreasing, right? Up here we have 2.9 times 10 to the minus 8, and then it decreases down to 2.0 times 10 to the minus 9, and then it decreases even more to 2.3 times 10 to the minus 11. So the more electronegative this X is, the higher our acid strength, the larger the value of Ka, right? And the reason why is because, again, electronegativity is the ability of an atom to attract electrons to itself. So if that atom X is more strongly attracting those electrons to itself, that's going to further polarize the bond between the hydrogen and the oxygen, resulting in a greater acidity, a greater tendency of that hydrogen to come off and to be donated to a base, right? So the electronegativity of X, right? The more electronegative X is, the stronger our oxyacid is. And finally, for oxyacids, the other factor that influences the strength of an oxyacid is the number of oxygen atoms that are bonded to X. So to demonstrate this, I'm showing 4 oxyacids on the screen that differ only in the number of oxygen atoms bonded to the atom that is bonded to the oxygen that is bonded to the hydrogen. So all the way on the left over here, we have perchloric acid. Then we have chloric acid right here. And then we have over here, we have chlorous acid, HClO2. And then finally over here, we have hypochlorous acid. So we have 3 oxygens bonded to that chlorine over here, 2 in the case of chloric acid, or excuse me, 4 oxygens bonded to the chlorine over here, 3 over here, 2 over here, and then 1 over here for hypochlorous acid, right? And so notice the relationship, right? In the case of perchloric acid, in which there's 3 other oxygens bonded to that chlorine, the Ka is strong, right? It's undefined. It's like division by zero, undefined, right? It's a strong acid, so it doesn't even really have a Ka value. There's a 100% conversion, a 100% ionization when you add HClO4 to water. And if you have HClO3, where there's one fewer oxygen atom than HClO4, there's a Ka value of 10, right? So it's a significantly weaker acid. And then it drops down even further when you remove that oxygen, another oxygen atom, to result in HClO2. That Ka is 1.1 times 10 to the minus 2. And then finally, for hypochlorous acid, this is the weakest acid of all of these four, coming in with a Ka value of 2.9 times 10 to the minus 8. So notice the pattern here. As the number of oxygen atoms decreases, the strength of the acid also decreases. Why do you suppose that is? Well, it's because oxygen, if you look at oxygen in the periodic table, oxygen is actually the second most electronegative element behind only fluorine. So because oxygen is so electronegative, it's going to draw electron density toward itself, and it's going to further polarize the oxygen-hydrogen bond, right? And if you're polarizing that oxygen-hydrogen bond even more, that's going to result in a greater acidity, because the more partially positively charged that hydrogen is, the easier it is to convert it into a proton and donate it to a base. So again, the more oxygen atoms that you have bonded to, in this case, the atom that we're calling X, the stronger the acid. All right, so we talked about binary acids, we talked about oxyacids, what's going on at the molecular level that is responsible for differences in acid strength among these various molecules that contain hydrogen. Now we're going to switch gears, and we're going to talk about another definition of acids and bases. So we've talked a lot about the Bronsted-Lowry definition of acids and bases. We've talked a lot about the Arrhenius definition of acids and bases, but there's a third definition of acids and bases, one that we haven't really touched on yet until today, and it's called the Lewis definition. So I'm going to take you on a little journey back to Acids and Bases Volume 1, the first stream that I did on this topic in early June. I'm going to show you a little clip from that video. So here we go. Which are the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis definition of acids and bases. Okay, so I did say that. I did say there were three definitions of acids and bases: Arrhenius, Bronsted-Lowry, and Lewis definition. So we introduced it in Volume 1, but we haven't really talked about it ever since then. So we're going to talk briefly about that. I don't have a whole lot of content related to Lewis acids and bases to show you, but I just want to show you that Lewis acids and bases is another way to think about acid-base chemistry, acid-base reactions, and so it would be important for us to discuss it before we end the topic. So let me take you to the whiteboard, actually. I'm going to take you guys to the whiteboard to introduce this topic. So here we go. So here we're at the whiteboard. And so I want you to consider this reaction right here, where we have H+, right, a proton, reacting with NH3, that's ammonia, which, as we know, is a Bronsted-Lowry base, to form the ammonium ion, which is NH4+. And I've sort of drawn it like this as a Lewis dot structure, sort of, with the hydrogen bonded to the nitrogen, with this pair of electrons sort of illustrating the chemical bond between the hydrogen and the nitrogen, like that. So a proton plus ammonia, and you get ammonium ion, NH4+. Now, we understand that... Hang on, I just realized I'm not even in the whiteboard myself. Okay, so we understand, right, that under the Bronsted-Lowry definition, the hydrogen is a proton donor. So that's the Bronsted-Lowry, I'm just going to abbreviate that, BL definition, right? The H+ is considered a Bronsted-Lowry acid because it donates a proton, right? The NH3 is considered a Bronsted-Lowry base because it accepts a proton. So the Lewis definition is kind of like, you can think of it as like flip-flop, like sort of the opposite of the Bronsted-Lowry definition in a way, because instead of focusing on the H+, for the Lewis definition, instead of focusing on the H+, we're actually focusing on the pair of electrons, right? So instead of thinking of it as a proton being donated to NH3, we could also think about this as an electron pair being donated to this H+, right? And this would be the Lewis definition. So again, I'll repeat that just to be clear about this. instead of looking at it from donating a proton, we're looking at it as donating an electron pair, right? So in this case, NH3 would be considered the Lewis base. It donates an electron pair. And the H plus would be considered a Lewis acid because it accepts an electron pair. So I'm going to go back to the PowerPoint real quick and sort of introduce this topic. So I'm going to move myself out of the way here, right up there. So under the Lewis definition of acids and bases, a Lewis acid is something that accepts an electron pair. It's an electron pair acceptor. And meanwhile, a Lewis base is something that donates an electron pair, right? So instead of talking about protons, now we're talking about electron pairs, where a Lewis acid is an electron pair acceptor and a Lewis base is an electron pair donor. And so what does this look like? Well, what are some molecules, for instance, that behave as Lewis acids? Well, boron trichloride is a good example, BCl3. Aluminum trichloride is another good example of a Lewis acid, AlCl3. And you might be asking yourself, well, what is it about BCl3 and AlCl3 that make them electron pair acceptors? And the answer is that it might rely on a little bit of prior knowledge, but back when we were discussing Lewis theory, Lewis dot structures and stuff like that, we looked at the octet rule, right? Where basically an atom is happy when it has 8 electrons in its valence shell, right? An octet, right? But we also saw that there are some exceptions to the octet rule, and one of those exceptions to the octet rule was the concept of incomplete octets. So there are some molecules, like boron-based molecules, aluminum-based molecules, that do exist in nature. They do exist in stable forms, but they don't have octets. So because they don't have an octet, what they have is an empty orbital, and that empty orbital is a very electron poor area that you can think of it like it really, really wants to have an electron pair come in and fill that spot, right? So it's an electron pair acceptor because it has that incomplete octet. It has an empty orbital just begging for an electron pair to come up and fill that spot. And so what would that sort of look like in the event of a Lewis acid base reaction? Well, that would look like something like this. So if you consider aluminum trichloride, right, AlCl3, reacting with NH3, ammonia, right? So what happens is you have this electron pair on the ammonia, which is the Lewis base, and that electron pair gets donated. It basically fills that empty orbital, right, that the aluminum has as a result of having an incomplete octet, and you form this molecule over here, which is like a combination of the two, and this is called the Lewis acid base adduct. So this is a molecule in which you basically connected these two smaller molecules together, right? So that's basically what a Lewis acid base reaction looks like, where you have aluminum trichloride, that's the Lewis acid, the electron pair acceptor, and NH3, ammonia, the Lewis base, the electron pair donor, reacting to form this adduct. And so if you start to think about this, we can understand that the Lewis definition of acids and bases, it doesn't really expand the list of potential bases, but it greatly expands the list of potential acids to include molecules that don't even have hydrogen, right? Because we're considering the electron pair and not the proton, right? Molecules like AlCl3, which don't have a single hydrogen atom in there, can be considered acids because they are electron pair acceptors. You don't have to have a hydrogen atom to be an electron pair acceptor, so you don't have to have a hydrogen atom in your molecule anywhere to be considered a Lewis acid. Okay, guys, so that is actually going to be it for the night. So I'm going to go back to this screen here. So, all right, that finishes the topic. We are done with acids and bases. So it's been a long journey. I've spent pretty much the entire summer just talking about acids and bases, doing my weekly streams. I'm really, really excited to be done with this topic and moving on to the next topic. The next topic that we're going to discuss is going to be aqueous ionic equilibrium. So we're going to be talking about buffer solutions acid-base titrations, the Henderson-Hasselbalch equation, polyprotic acid titration curves, and everything in between. So I'm really, really excited, and I hope you guys are excited as I am to jump into that content because we're going to do so starting next week. So that's going to be what, Sunday the 8th. So yeah, very, very excited for that. Thank you everybody who have been watching the streams, watching the videos in the playlist, leaving likes, leaving comments. I really, really appreciate your attention and your support, and I look forward to bringing you excellent chemistry content in the future. All right, everybody, take care.